as a mathematician, all of us, I mean, most of us we are rather wary about figures. And personally, too, I was totally afraid of them until one day something clicked in my mind when somebody told me about the logic of figures. Now, that's something which I don't think we learn in school because it's very basic what they do teach us there. So lots of us are scared of figures. You are a wizard, and you've come as the son and the grandson of professors. So what we would like to know from you is why is it that you consider, I mean, you're a professor in Cambridge doing pure mathematics, whatever that is. So why is it that you consider mathematics has a wider reach and a universal appeal and a universal language?
Well, it works as a universal language because it describes the world around us. And it describes the phenomena that we experience, at least some of the phenomena that we experience in the world around us. And it's a way of characterizing phenomena and analyzing them, of reducing them to certain qualities that we can then talk about, calculate with, we can deal with. So mathematics is a science about the world around us, but more interesting than that, because the world around us, as it were, we have studied quite well for the last couple of thousand years. The last couple of centuries, mathematics has gone well beyond understanding the world around us and understanding things that we can generalize from the world around us. So we talk about numbers now that you don't know about, that you can't think about. Numbers that are larger than infinity, for example. And when you talk to most people about, oh yes, there are numbers larger than infinity, there are different sizes of infinity. And mathematicians are very casual and very calm about those sorts of phrases. And the ordinary public looks at you as if you were completely mad. And we all understand 2- and 3-dimensional space. Planes are 2-dimensional, objects are 3-dimensional. But there's no reason to restrict ourselves to 3 dimensions. We can talk about 4 and 5 and 250, and indeed infinitely dimensioned space. So mathematics has this extraordinary ability, because it is abstract, because it follows ruthlessly the rules of logic. It has this ability to take our everyday experiences and the world around us and generalize it. And the miraculous thing, this is what nobody understands, the miraculous thing is that as we talk about more and more abstract things, it turns out they have applications in the world around us. Often very surprising applications, but applications in the world.
For instance?
Well, you might just be old enough at 30 plus, you might just be old enough to remember...
30 plus?
Well, aren't you about 30?
Four times that.
Yeah, I mean, I've been 39 for, the last 40 years. So, and see no reason to change. So,
yeah.
So, but you might remember long ago when we had old-fashioned phone systems that you could hear, sometimes you could just about hear another conversation in the phone system. Well, that was because those old kinds of phone systems used a thing called bandpass filters. And that meant you could get many different conversations down one wire. That was a technology that was sorted out in the late 1940s by somebody who actually became a professor of mine in Cambridge and who was an awesome, awesome character, a man who had survived the concentration camps of Nazi Poland. And he had solved the problem of bandpass filters because in Poland he had been taught proper old-fashioned, what we call classical analysis. And he knew some theorems of Euler on what's called continued fractions. And he could apply the continued fractions of Euler, first written down about 1740. Completely useless, just a totally ridiculous way of manipulating numbers. And continued fractions enabled him to model the bands that you get in a telephone to enable many conversations down one wire. And there's a beautiful example of something that had to wait 3 centuries before it became useful. And then
how does that connect with mathematics?
Because what Euler did was mathematics. The continued fractions. Euler's a great mathematician of the 18th century, one of the most prolific mathematicians of all time, and he developed this theory, this mathematical theory of continued fractions, which then turned out to be useful, but 300 years later. And it's literally lay there, apparently useless for 300 years. And this happens again and again and again. But what I want to talk about today is how actually in the last generation, well, the conclusion I want to come to today, if everybody hasn't left by then, is that mathematics and its relationship to its applications has changed very profoundly in the last generation. The last 20, 30 years, mathematics is becoming a terrifyingly new, different subject. And people need to be aware of this.
Well, I just have one last question before I leave you to your isolation. I'll leave you alone here, if you don't mind.
Yes, thank you.
Yeah. Computers. Again, an application of mathematics?
They are a wonderful new technology, and that's just straight engineering, straight clever electric engineering. But well, that's the hardware. What makes a difference with computers is the software. And the early software down to about 10 or 15 years ago, was mostly written by computer scientists who were adapted in computer languages and so on. The cutting edge of computing today, which is what is really frightening, the kind of things that Facebook and Google can do, and the kind of thing government spy agencies can do.
Interfere with our privacy.
And all of that is done using algorithms and very clever analysis that is written by mathematicians. And it's stuff that only mathematicians understand. It is completely untransparent. And the general public and governments have no idea, no capacity to control this, to know what's going on. And indeed, they just simply stand back and let this happen. And this is a whole new kind of mathematics. So it's not the computers that you should fear, it's modern day software and the kind of algorithms that computers now use. And that's new territory.
I shall leave you to your talk. We'll be back later.
Okay.
I'll be here.
All right, so there's going to be at least the two of us.
Of course.
Okay, well, now...
If you want some water, it's here.
Okay, I was asked to talk about mathematics as a universal language, and I could talk for days about mathematics as a universal language because there are so many interesting aspects in which mathematics is a universal language. However, I will admit to feeling something of a fish out of water at a literary festival because I'm not a writer. I don't write as an art form. I am, in fact, profoundly unliterary. I do not have a literary mind at all. I remember reading poetry at school and thinking, well, that's interesting, and that was it. I haven't read poetry. I very rarely read novels. I'm not a literary sort of person. So if you feel that I really don't belong here, I'm entirely sympathetic with you and I'm not going to object to you. So just be warned that I'm aware that I, in one sense, don't belong here because I am not a literary person. I don't have a literary mind. I write a lot, but I write very tedious textbooks in mathematics and things like that, which sell 5 copies if they're lucky and are read by 2 people, one of whom is my mother, bless her, and that's it. This is a very restricted kind of technical literature. But I want to argue, I want to try and persuade you that mathematics is a language, and it is an interesting language, and there are some consequences of the nature of mathematics as a language of which you should be aware, you as people who are in literature, who understand literature, that you should be aware, and it's part of the literary world as well as part of the scientific world. After all, mathematics, as I was just saying, describes the world. It describes aspects of the world. It describes, we choose some aspects that we use mathematics to describe. There are other aspects we don't choose mathematics to describe. It's very good at talking about some parts of the world, and it's completely inadequate to talk about other parts of the world. I was going to say mathematics, for example, doesn't talk about anything to do with love in any way, shape, manner, or form, but that's absolutely false. Have any of you ever heard of the program that lots of young people have on their phones called Tinder? Yep. In which there are mathematical algorithms which attempt to match boys with girls, men with women. And these algorithms are extraordinarily sophisticated and getting more and more sophisticated as Tinder becomes more popular and has more data to develop. And it is based on a series of absolutely brilliant, unbelievably dangerous algorithms. Because these algorithms could, if Tinder wanted to, they could create eugenics. They could actually put into these algorithms that these kind of peoples won't match up. And they can manipulate, as this becomes more popular, they can literally manipulate the eugenics of the human race. So when I say mathematics can't model love, well, actually, mathematics is starting to even affect how lots of young people in the Anglo-American world and in Europe, how they start to match up. And there are lots and lots of Tinder marriages and lots of Tinder babies. And if that isn't manipulating love, then I don't know what is. I admit you can't write a novel in mathematics. A novel written in mathematics would have an exceedingly small readership and would not be a pleasant novel to read at all. But mathematics does convey immense cultural meaning in the way that it chooses certain things to talk about, and to talk about them, to try and analyze them, using certain kinds of terms. So there is imbued in the kind of choices that mathematics makes, there is in that an enormous amount of cultural choice. And those are cultural choices which today, 2019, affect your life 24/7, 365 days a year. You may not know it, you may not sense the mathematics, but it is there and it is affecting your life all the time. There are those who understand mathematics, who've experienced doing mathematics, who understand that mathematics can give rise to a kind of ecstatic beauty and revelation. And it is a commonplace amongst mathematicians that we talk about the beauty of mathematics, and there is a particular kind of ecstatic beauty, an experience of ecstatic beauty, or of, often people use religious terminology like revelation in mathematics, which is amongst the most addictive and intriguing human experiences. And if you ask many people why they do mathematics, their answer will be because of the beauty of mathematics. I went up to Cambridge to read physics. In my first year, I took a mathematics course, and I was so overwhelmed by the beauty of the mathematics that I was taught that I promptly switched from physics to mathematics. And it was literally the hunger for that aesthetic experience of beauty which I saw in mathematics. Now the problem is I can't explain that beauty to you, because the mathematics that most of you, unless you're a professional mathematician, the mathematics that most of you have experienced was school mathematics, and school mathematics is to real mathematics like spelling is to poetry. That is useful to be able to spell, to read and write, but spelling itself is not poetry. And it's even handy to know how to spell in order to read poetry, but knowing how to spell is not to read and understand and be moved by poetry. And mathematics is much the same. The only difference is that you can learn to spell in a year or two when you're 10 or 7 years old, whereas it's going to take you 15 years of education to get up to a level where you will begin to see the beauty of mathematics, which means it's highly restricted, but it is still a form of expression, a way of talking about the world that can take you to experiences which you would like to articulate using words like beauty and revelation. Indeed, to the extent that through the ages, mathematics has regularly been described as a means of communication with the divine, as a representation of God, choose your God, but a representation of God, a manifestation or an articulation of God's thought. This is a commonplace in the history of mathematics. Indeed, I'm going to be talking a little bit about it in 2 days' time when I'm going to give a talk about mathematics and God. That was not the original title I proposed, and very, very naughtily, they said, nah, let's not have a boring subject, let's have something more interesting. So they've thrown me in on the deep end to talk about mathematics, mathematicians, and God, and, well, I'm going to try to, because historically, and indeed if you talk to mathematicians today, they talk about the experience of mathematics, the purity and the transcendental truth of mathematics in a way that sounds an awful lot like a religious experience. So something that can give you a vision of transcendental beauty, something that can claim to be a language that all people can understand and can model phenomena of all sorts through all time, that sounds to me like it's a proper language. It's a language which has a grammar, it has a language which has its own imagery, it's a language which has its rules of composition. So any way that you try to describe what ordinary language is, I can find ways of seeing mathematics as a similar kind of language. But it is actually so much more than just an ordinary language. I have a list of some of the ways it is so much more than just an ordinary language, and I want to take you through a couple of those items in the list because I want to leave you frightened. I want to leave you scared about where we are in 2019. First of all, it's the most ancient of languages that we can still speak and understand today. This is wholly unexpected by most people, but I can go back to Greek mathematicians. You're fiddling with the volume back there. I can go back to Greek mathematicians and I can read their mathematics and I can understand how they thought and what they thought they were doing. I can also read ancient Greek literary authors like Homer or Herodotus, and Homer and Herodotus can give me some idea of Greek society and Greek relationships and Greek behavior and all sorts of aspects of the human world of the Greeks. But their politics, their morals, their social values, their legal system is so different from our own. There is that classic phrase, the past is a foreign country, and indeed the past of the ancient Greeks is an extraordinarily foreign country. You can read their literature, you can read their philosophy, and you will struggle deeply to understand the content, to understand really how the Greeks thought. We get some sort of vague idea, but it is at best a vague idea. Can we really understand how an ancient Greek would read the myths about Achilles and how they would understand that mythology? The ancient Greek knew that Achilles was a mythological figure. They knew that this was fiction. They knew that the story of Homer was not true in some mechanical sense, but they took it to be true in some mythical and moral sense. Do we really understand how that works? We can get a very vague vision of it, but it's only a very vague vision. Do we understand how the Greeks thought about things like death, how they respected the dead body, even the dead body of their enemies? When Achilles drags Hector's dead body around Troy, this is regarded as shocking and disgusting. And the Greeks turn against Achilles for this profoundly immoral act. Well, we can say the words, but do we really understand how the Greeks felt about the respect that was due to the dead body of your enemy? Well, if we look at how we behave in the 21st century, the answer is no, we don't, because we certainly don't behave like that. We don't even understand the Greek attitude towards sex. You'd think that was something that was fairly universal, but if you read Plato's Symposium, where modern authors have recognized something that authors 100 years ago didn't want to recognize, which is that Plato is talking about what we call homosexuality in the Symposium, we find it very difficult to understand what Plato is talking about, because he's talking about male-male relationships in ways that we would model as homosexual, and Plato would absolutely say is not homosexual, but is perfectly normal and heterosexual. It just happens to be men with men. And we would find that, we do find that, very difficult to understand and very difficult to model. So when I look back at ancient Greek civilization, I choose that one because it's the one I know about. You could do the same with every other ancient civilization. Their literature gives me some window onto their society and their behavior, but can I understand in detail and in depth how they thought? Very often I think the answer is no, we cannot. When I look at a mathematician like Hippocrates of Chios, who in 430 BC wrote the first concatenated chain of theorems, where one theorem depended on the previous theorem, which depended on the previous theorem, which depended on the previous theorem, which is one of the earliest and most extraordinary bits of mathematical thinking, I can follow the text and I can understand exactly what Hippocrates of Chios was thinking. I can understand why he came to the conclusions he did. I can understand the limitations that he drew. I understand the limitations on what he thought he had proved. I can actually get inside his mind and I can read with complete precision. Now, with Hippocrates of Chios, I have about 15 pages of his text. 150 odd years later, I have Euclid, and I have 300 pages of his text. And Euclid, I have so much of his text, I can even find a sense of humor in Euclid. I can actually find where Euclid is metaphorically writing, and then he looks up with a smile on his face, and yes, isn't that nice? Look what I've done. Proposition 10, number 1, okay, book 10, number 1, if you read it and read it carefully and read it again and again, you actually can see that Euclid finished that proposition with a huge grin on his face. He was really pleased with that. Proposition 12.2, it's one of the most difficult of Euclid's bits of mathematics, but he reduces the difficulty of it because there are two cases, and instead of writing 10 pages on the first case and 10 pages on the second case, he flips the second case so it becomes derivative of the first case, and he doesn't have to prove anything extra to get the second case. And when he flips it, you can feel Euclid's pleasure at the elegance of this. But I don't need to do all of this work again. I can just flip it, and you see it's another type, another version of the first case. There's enough of Euclid that I can actually feel in the cold mathematics. I can feel his own intellectual discipline and his own intellectual pleasure. You can tell in books 7 and 8 that Euclid is bored out of his skull. This is long, hard, technical maths, at the end of which you get nothing of any great interest, but you kind of got to work your way through it because you have to have a complete theory of non-commensurable magnitudes. So, boring, I'm going to give you the complete theory of non-commensurable magnitudes. Thunk, there it is. Can we go and have dinner now? Because that was really dull. And you can feel Euclid's lack of interest in this. I can actually not only understand his mathematical reasoning, not only can I understand his logic and the constraints of his logic, I can understand his intuitions. I can understand it as if he were speaking to me in my own native language. That's how extraordinary the language of mathematics is. And this is something that is more than 2,000 years old. And the magic of this, what is difficult to comprehend, is that Euclid has been understood this way, has been revealed to people with this kind of clarity for the last 2,000 years. People in 1500 and in 1000 and in 500 AD could read Euclid and get this message, get this understanding, feel the depth and the intimacy of Euclid's reasoning and his thinking. And I hope it is correct to say, will somebody please check on this, in 2,000 years' time, they will still understand Euclid, just as we can understand Euclid today. The timelessness of that language will enable people in 2,000 years who will live in a world incomprehensible to us. I find it pretty difficult to imagine what's going to happen next week, let alone what's going to happen in 60 years' time. And in 2,000 years' time, I mean, don't be silly, we can't imagine what the world is going to be like in 2,000 years. But they will still be able to understand Euclid. That's a remarkable kind of language. And that kind of language, that is unique, to have that kind of understanding. I can go much further than just understanding Euclid. Because Euclid, after all, is the origin of, or one of the origins of the Western mathematical tradition. So, of course, I should be able to understand Euclid. But I can go so much further, because I can read ancient Chinese mathematics, mathematics with which I have no cultural or historical connection whatsoever. Chinese mathematics peters out as an autonomous, independent tradition in the 15th, maybe 16th, the 15th century. It just loses steam, and there is very little new mathematics in the Chinese mathematical tradition. It begins in probably the 2nd, maybe the 3rd century BC, and we have lots of texts now in recent years. More and more texts of very early Chinese mathematics have been discovered, and we understand more and more of how early Chinese mathematics developed. It's a way that's completely different from early Indian mathematics or early Greek mathematics. It's autonomous, completely different, and with only a little bit of labor, I can understand how early Chinese mathematics and mathematicians thought. They have a different language of mathematics, different concepts of mathematics. They have different ways of proving things. Of course, they still add, subtract, multiply, divide, find the area of squares and circles and so on. They're still looking for the same knowledge, but the way they do it is very different from either the Indian tradition or the Western tradition. And I can understand it. I can come to an understanding of something which is culturally and historically completely disjoint from me. And I've got a pretty good understanding of how those early Chinese mathematicians thought. It gets worse, because we can actually understand past mathematics with an absolutely extraordinary quality and depth. And now I want to really make you all hate me, because you've all heard about Pythagoras. And you've all heard about, you learned at school Pythagoras' theorem. Do you remember it? Most of you don't want to remember it because you didn't like maths at school, right? If you're like most people, you didn't like it and you hated Pythagoras' theorem. And you remember that Pythagoras was supposed to have discovered, to have proved Pythagoras' theorem. And one of the other things that happened as a result of Pythagoras' theorem was that the ancient Greeks discovered irrational numbers. And this caused great horror amongst the Greeks because irrational numbers seem to go against their whole concept of number. Okay, do you remember these stories from school? Well, we can read the ancient texts with sufficient care and precision to know that everything I've just told you is false. There is no evidence that a man called Pythagoras ever existed, and if there did exist a man called Pythagoras, you can speculate if you want. If there did exist such a man, we have no idea what he did, but I know that he did not discover the theorem of Pythagoras. Almost certainly the Greeks knew and were using the results that we call the theorem of Pythagoras 150 years before Pythagoras didn't live, as it were. We know that the ancient Sumerians knew the theorem of Pythagoras 2,000 years before Pythagoras didn't live. 2,000 years. As far back as the turn of the first millennium, the life of Christ, for example, or Augustus and Roman, the Roman emperors, as far away as those people, that's how long before Pythagoras that the ancient Sumerians knew the theorem of Pythagoras. I'm coming back to that in a minute. And I can reconstruct ancient Greek mathematics with such precision, with such care, I can understand how they knew about numbers, what intuitions they had about the properties of numbers, that I know, I can show that what Pythagoras, or somebody soon after Pythagoras, discovered was not irrational numbers, but something completely different, and something which did not surprise or offend or cause horror to the Greeks. The Pythagoreans did not discover irrational numbers. Worse, their concept of number was such that they could not discover irrational numbers. I actually can know their thinking so intimately that I know what they couldn't do, what was outside the envelope of the possible imagination of a Greek mathematician. Think about the power of that language that it can convey to me over 2,500 years, that much information, and that much information about a mathematician about whom I don't know if he lived, I don't know what politics he liked, I don't know, was he gay, was he heterosexual, was he a communist, was he a conservative, did he like to drive Japanese cars, did he like to drive Italian cars? I have no idea. I know virtually nothing about any of these mathematicians, but I can know one aspect of their minds so tightly, I can know the constraints on their own imaginations. I said that the ancient Sumerians knew the theorem of Pythagoras. We have a tablet dated about 2500 BC, might be 2700 BC, might be that old. It's a tablet where somebody, I know nothing about the author, had a blob of clay, rolled it into a ball, slapped it down to make a flat sort of pancake. I know that because his handprint, his or her handprint, is actually left on the clay tablet. And then that person drew 5 lines, and wrote down 2 numbers. 5 lines, the tablet is about this big. It has 5 lines, a square, and the diagonal of the square, and then 2 numbers, one in the middle of that tablet and one at the top. And with that tablet, I know that the author knew the theorem of Pythagoras, was able to calculate the value, the numerical value of the square root of 2, and that value in the middle of the tablet is the square root of 2 to 6 decimal places. No practical purpose in 2500, 2800 BC needed the square root of 2 to 6 decimal places. That's a mathematician, or somebody like a mathematician, who is absolutely delighted with this relationship, so delighted that they make a ball, slap it down, and with 5 lines and 2 numbers show you, I have this relationship, the relationship that we call the Theorem of Pythagoras. I know nothing about this person's context. I don't know this person's sex, education, age, nothing. But I do know what they were thinking, and I know exactly how they calculated the square root of 2 to 6 decimal places, because that number on the top of the tablet tells me the method that they use to do this calculation. So here's somebody about whom I know nothing except this one pinprick of information, but that pinprick of information is extraordinarily deep and extraordinarily precise. Can you imagine a language that gives me that kind of intimate knowledge of somebody's thinking? I'll go one step further. Let's hope that one day we find life not on this earth. Let's hope that one day we find little green men on Mars, or on some planet we've discovered now 2,500, well, last time I looked, we had discovered about 2,500 planets around stars near us in the galaxy, of which a couple of hundred planets are in what they call the Goldilocks region of they're not too big, they're not too small, they're not too hot, they're not too cold. Water might exist on those planets, and that means the conditions of life might exist on those planets. That's just near us in our galaxy. Of course, there are billions of stars in the galaxy, and probably around each of those billions of stars, there are dozens of planets, and there are hundreds of billions of galaxies, each with billions of stars, each with dozens of planets. Do the multiplication. There are a vast number of possible locations where there might be other life in the universe, and who knows, there might even be intelligent life. What will happen if one day we are visited by little green men, by aliens? Will we be able to communicate with them? Absolutely not. They will have no common experiences with us that will enable us to find any vocabulary that is the same. They may not even be life forms based on carbon. Our life form is a carbon life form. It's perfectly reasonable to have a life form based on silicon. They won't have sensory systems like ours. They won't have brains like ours. They may not have reproduction and life and death like we have. In what way could we possibly communicate with some other species that has a technology sufficiently advanced, way more advanced than ours, to actually visit us? It's really simple. I will put 1 pebble on the table, and then 2 pebbles on the table, and then 3 pebbles on the table, and then my alien will put 4 pebbles and 5 pebbles, and then I will put 2 and 3 and 5, and the alien will, in whatever way the alien has, nod happily, and then put 4 pebbles and 1 pebble together, and we will agree on addition. And then I will draw a circle and a line, and then I will draw more bits of geometry, and my alien, whatever means they have of being present, will then be able to draw circles and lines, because geometry, space, and numbers, individual objects, are going to be something that the alien will understand, will probably know better than we do, in fact, and we will quickly be able to learn how to communicate mathematics with the alien. Will we ever be able to discover or to communicate honor and dignity and hope and passion to the alien? I have no idea. I have a sneaking suspicion we won't be able to convey honor and dignity and love, because these are such human values. But we will be able to talk to the alien, because we will be able to communicate mathematics. And that's the window that we will have on even something so alien as mathematics. Sorry, something so alien, so different from us, as a species that has no common experience from us. There is, however, also a dark side to this. And this is something which mathematicians are only just now, and very few of them, beginning to notice. Mathematics is a universal language and has been a universal language. And because of its universality, both in time and global reach, it also is a language that has, in effect, no restrictions on it. Part of the reason for this is that most people don't understand mathematics. So the mathematicians can talk to each other, and nobody really can come along and oversee them. Even in ancient Greek times, you get people like Aristotle, dear old Aristotle, such a terrific chap. I mean, what an amazing guy Aristotle was. But, you know, he couldn't add, subtract, multiply, or divide two-digit numbers. He's the son of a medic. He was a biologist. He really didn't understand maths. And you can see one of the reasons why Aristotle and Plato didn't get on was that Plato did understand mathematics. Aristotle, poor guy, he just didn't get it. Okay? And as a result, when he talked about mathematics, he talked complete gibberish. And he really did. We're not supposed to say rude things like that about mathematics, about Aristotle, because he's this great titanic figure. And he is this great titanic figure. But when it came to maths, I'm sorry, he's an idiot. And it shows. And it shows regularly. Because mathematics, even to the ancient Greeks, was restricted to a very small group of people who knew it and understood it, mathematics has never been open to control, to surveillance. If you think even about chemistry, about biology, even about physics, governments regularly have tried to legislate or to control what biologists, chemists, even physicists have done. And indeed, since physicists invented the atomic bomb, physicists have realized that physics needs ethical constraints. They lost their virginity in August of 1945, and they realized that they have to operate with ethical constraints. This has not occurred in mathematics. Mathematics is an unrestricted language, but much worse than that, because mathematics grows as an onion grows in layers, where past mathematics is not seen to be wrong, we build on it. Euclid is still true today. We've just done a lot more than Euclid. When I look back at 5th century AD or 5th century BC mathematics, I can see the truth in the mathematics, and that truth has been maintained all the way down to today. So the language of mathematics, the ethos of mathematics, has not been challenged and not been changed. Mathematicians are a tribe, a culture, which has a history which they trace back to the 5th century BC and which has not been overthrown or contradicted and has not been restricted. Mathematicians regard themselves as, quite properly, if you will, free citizens, free to do whatever they like. That sounds lovely, that sounds good. Until you begin to look at the world around you and you think that in your smartphone, and admit it, if you're under 50, you are surgically attached to your smartphone. Okay, you don't go out of the house without your smartphone. Your smartphone is next to your bed. You're so attached to it. You can't live without your smartphone. And behind your smartphone, there are probably hundreds of thousands of mathematician hours that made the technology of your smartphone. You use email, you use Google, you use Facebook. I hope you don't use Facebook, but you do. And Google and Facebook and hundreds of other corporations have vast capacities to spy on you, to learn about your life, your preferences, your behavior, and they use that data, which they collect using unbelievably sophisticated algorithms written by mathematicians, They use that data, they analyze that data to find out everything about you. They now can find out that women are pregnant before women know they are pregnant. They can look at behavior patterns and actually discern women who are pregnant before the women know it. They can find out your voting preferences without ever asking you who you vote for, and they can find out your racial prejudices, your insecurities, your racial insecurities, your economic insecurities, your social insecurities by the use of brilliant, subtle algorithms written by mathematicians. And these corporations and governments are building a vast capitalism of surveillance using the algorithms written by brilliant first-class mathematicians who are being paid vast sums of money and who have no idea, no ethical conscience about what they are doing. The largest employers of mathematicians in most of the civilized world, in America, in Japan, in France, in Germany, in England, I bet, I don't know, but I bet in India, the largest single employer of mathematicians are government spy agencies, because the spy agencies need the mathematicians to write the algorithms to spy on you and ultimately to control your lives. We have a whole new world of mathematics. It's only a generation or so old. We have a whole new world of mathematics that is done by mathematicians who have inherited this pre-ethical vision of their mathematics, who exist in a world without social responsibility. The universality of the language of mathematics is going to imprison you. It's going to allow you to be manipulated and imprisoned. And governments have no way of stopping this. They do not have the capacity to regulate mathematics. If this scares you, I hope it does, because I look at what my students are doing and I look at the careers that they are going to have, and I have to tell you, I'm terrified. I'm terrified because of the power and the universality of the language of mathematics.
I think you know too much, Professor, because I'm not afraid, I'm not terrified, and I don't see any reason to be. You've got a passion, you're flirting with figures, with mathematics, and I would like to get into your mind to see how it ticks, but very difficult. Would you be prepared to answer a few questions?
I'd be delighted to.
Hello, sir. Welcome to Kerala.
Thank you.
Actually, my question is somewhat political. I don't understand my bigger mathematical theorems and all. I have heard of a guy who is a very brilliant mathematician, Robert Mercer.
He's not a brilliant mathematician, he's an evil billionaire.
Yeah.
Who employs brilliant mathematicians. He's a fascist.
Yes.
And he financed Cambridge Analytica, which swung, because of this scraping of data,
Yes.
which swung the Brexit referendum. Probably 5 or 6% of the vote was swung by Cambridge Analytica. And the Trump election, in the states where Trump won by narrow margins, undoubtedly Cambridge Analytica swung that vote by more than 4%.
So my question is, we are considering mathematicians don't have such political lineages. They don't have that kind of a humble people who are working in solitude. So my question is, can mathematicians be classified as conservatives and liberals? Now the question is about the digital world is actually conquering the real world. So there will be a predatory business models every time. Our voting, our eating, everything will be conquered by this digital world. So mathematicians are the real geniuses, maybe evil geniuses, Lucifers behind these thoughts. So can we classify them in a political manner, like liberals and maybe libertarians?
Most mathematicians are fairly liberal, but they are politically very naive. So you will ask a mathematician, who do you vote for? And they'll tell you, oh, I vote for X, and they will have reasons for voting for X. But if you then say, is the mathematics you do political? And most of the mathematicians will answer, but of course not. I do mathematics. It's not political. And trying to convince mathematicians that maybe 50 years ago, mathematics wasn't political, but since 1990 or so, mathematics has become increasingly and intensely political because it's used for political purposes. I can tell you that is an uphill struggle. It is very difficult.
Respected Professor, actually I was taught and I got certain idea regarding beauty as a combination of golden ratio and symmetry and those things. But you are telling that mathematics is a universal language, but it got certain limitations based on rigorous mathematical framework and all. But beauty lies, as in the canonical universal language scenario, beauty lies in the eyes of beholder.
Of course it has the restriction that we choose what to mathematize, but we choose more and more things. We discover more and more things that we can mathematize. And would you believe that people's political behavior can be mathematized and can be understood from other aspects of what they do on Facebook? The answer is yes. So increasingly we find mathematics can be applied in domains where we never thought it could be applied. So that's why it has no constraints, because mathematicians will use it wherever they can. In a sense, that's good, but if you do that with no ethical sense of responsibility, you have power without responsibility, and we know that's dangerous.
Thank you for the great talk, Professor. My question is, if you look at the recent developments like AI and genetic algorithms, things like that, they, to me, seem to be moving from the structured, analytic, algebraic way of doing things and somehow feeding a problem into an AI system and it solves it for you. So, is that understanding correct? That's my first question.
The AI is solving the problem because the mathematicians have taught it how to solve the problem. We forget that AI is completely stupid. Its only intelligence is the mathematical program, the mathematical formulae that have been given to it by mathematicians. So AI is unbelievably clever because it has underneath it unbelievably clever mathematics. So, as it were, it is as intelligent as the mathematicians who program it.
Last question.
Thanks, Professor, for the quite illuminating talk. I have a question about how mathematics is linked or interlinked into logic. So, for example, is math a subset of logic and what the relationship is? Or can mathematics be disproved by logic?
No, mathematics is a superset of logic. Okay. So mathematics cannot go where logic does not go, but mathematics can say things beyond logic by developing pure logic into more and more abstract structures. So mathematics is a superset, not a subset of logic. There's logic, there is mathematics. But you don't get mathematics without logic. I think we should end because there are other people who want to...
Yes, I think that should be the last question. Thank you very much, Professor.